Hello everyone, my name is Ben and this is Math with Ben. Today I put up a poll on the Instagram to see what video you guys wanted me to make next. I've been reading a little bit about a subject called real analysis, and I put on Instagram to see if you guys wanted more calculus videos to come out soon, or for me to start a series on where I learn real analysis. So this is me learning a subject along with you guys and me talking about it and what I think is interesting, rather than me teaching a subject, because I don't know a lot about it and I'm just learning. So I'm reading this book that I got from the math library at the University of Vermont called An Introduction to Analysis, 2nd edition, by William R. Wade, and that is the book I will be basing my notes and videos off of. It's a pretty good book. I'm a little bit into the first chapter. There's a lot to learn about in real analysis, and so let's talk about it. Real analysis is the study of real numbers. It's also the study of the structure of calculus. It goes into depth about proving things about the real numbers and also proving things about calculus. And there's real analysis in one variable that proves things in one variable calculus, which is calculus 1 and 2. And it proves things about multivariable calculus, which is calculus 3. And I'm really excited to learn all of this. So what I am on right now is Chapter 1, Section 1.1, which is ordered field axioms. Mathematicians use these things called postulates and axioms that are set in stone and defined things in math that you can use to prove theorems, right? So there are a list of axioms that I will talk about in this video that will prove pretty much every theorem in algebra, that you can use to prove pretty much every theorem in algebra, and it's really, really interesting. So let's start. So we're in this section 1.1, which is the ordered field axioms. So the first thing we learn about is the empty set. So the empty set is denoted by this circle with a line through it, which is a 0 with a line through it. It's the empty set. And the empty set, you can see on the right, is the set with nothing in it. It's empty. There's no elements of this set. A, epsilon A, that's a lowercase epsilon, is it's a lowercase epsilon, but also a sort of different version of epsilon used in math. A, it means an element of. So A is an element of the set A in this case. And then a line through it means A is not an element of the set A. Now this you learn in other classes, linear algebra, fundamentals of mathematics. This is just some basic notation around what we will be using. So there are two ways to define a finite set, and we're going to use an example. So the example here is x squared equals 1. Now, there's a list of numbers that satisfy this expression. And the first way to define a finite list with all of those elements is 1. List every element directly. So in this case, it would be the set containing 1 and negative 1. And the second way is sentences or equations. So in this case, the set x such that x squared equals 1, right? That line through the middle there means such that. Some people use a colon. But that just means x such that x squared equals 1. It's every x that equation satisfies, or that satisfies that equation. So 1 and negative 1. This little thing here, it's not less than or equal to. It's more rounded than that. It means A is a subset of B, a subset or equal to B with the line under it. We'll get into proper subsets in a little bit. But this just means that if A is a subset of B, if and only if every element of A is also in B. Definition, A is a subset of B, but there is at least one element B in B such that B is not in A. A is a proper subset of B. This is what I was just talking about, right? And you can see in the notation that there's no line under it. This just means that every element of A is in B, but there are no elements of B that are in A, besides the ones that are in A. So this just means that A is a proper subset. So it's strictly only A, and nothing extra from B is in it. Here's another definition. So real analysis is a lot of definitions and a lot of going over those definitions. Two sets are said to be equal if and only if A is a subset of B and B is a subset of A. This just means every element of A is in B and every element of B is in A, so therefore they are equal. Union, denoted by this big U. The union of two sets A and B is the set of elements X such that X belongs to A or B or both, notated A union B. This just means there's the set that has every element of B, every element of A, or every element of B. So it contains all elements of both. The intersection. The intersection of two sets A and B is the set of elements X such that X belongs to A and B. So it's only the set that contains elements that are both in A and B. So we can see this here with these two Venn diagrams, right? The one on the left is A union B. So every element of A, every element of A and B, and every element of B. And A intersect B is the only elements that are in both. So let XY be sets. The Cartesian product of XY is the set of ordered pairs, is defined by X cross Y. This little 2 colon with the equal sign means is equal to by definition, and that's all it means, equal by definition. So X cross Y equal by definition to the set X comma Y such that X is in X and Y is in Y. I try and separate the little Y's and the big Y's and the little X's and the big X's the best I can, but it's hard. So what is a relation? A relation on XY, X cross Y, is any subset of X cross Y. So it's any set that contains elements of X cross Y. So let R be the relation on XY. The domain of R is the collection of X in X such that XY belongs to R. When XY is in R, we shall frequently write XRY. This just means X relation Y. So a function, right? Just a lot of definitions, a lot of, interesting and sort of strange math to think about. It's more logic than anything. It takes a lot of thinking. I encourage you to pause this video and look up anything you need to look up, and think really about what this means. A function f from x into y, notation f colon x arrow y, is a relation on x cross y whose domain is x. Notation dom f is equal by definition to x, such that for each x in x, there is one and only one y in y which satisfies xy in f. In this case, f is defined on x, and call the y value of x at y value of f at x. Notation y equals f of x. And this is the notation you learn in algebra and calculus and whatnot. And this is a really cool way to think about what functions actually do, right? They're mapping inputs onto a different space containing outputs, right? And commonly in algebra and calculus, and what you've learned up until this point in math, is that every function maps some value in the real numbers to another value in the real numbers. But there are functions that can change what set you are using, right? There are functions that can map real numbers onto natural numbers, which is really cool to think about. So our line, there's a specific name for it, but this R with 2 lines through it is the set of real numbers. So assume R is a field, which means it satisfies the following postulate. So this is where we get into the first postulate of math, really, right? There are ones before this, but this is the one, really one that is the defining postulate for most of algebra. So a postulate is just sort of a list of axioms. So this one is called the field axioms. There are functions plus and times defined on R2 by definition, or equal by definition, R cross R. This just means that the plane R2, which is the XY coordinate system, is the cross between the real numbers and the real numbers, which is really cool. It's basically R squared. It's a plane that contains real numbers in every direction, which satisfies the following properties for every A, B, C in R. 1. The closure properties. This means that a plus b and a times b are both in the real numbers. This is closure of addition and closure of multiplication. 2. The associative properties. A plus b plus c is equal to a plus b plus c, and a times b times c is equal to a times b times c, right? And this is, of course, true. The commutative properties, a plus b equals b plus a, and a times b equals b times a. And these may seem relatively simple and obviously true, but they're very, very difficult to prove, and we'll get into that later, I'm sure. I'm not an expert on this subject, and I haven't finished the book, but it's really, these are some cool ground laws to think about for all of math, how this basically defines algebra and what you can do. The distributive law, a times b plus c is equal to a times b plus a times c. 5. Existence of the additive identity. So this states there is a unique element 0 in R such that 0 plus a is equal to a for all a in R. This says in any field, right? We said the R is a field, and these are the field axioms. So any field of numbers is required to follow all of these axioms. And this one states, in any field, there must be an additive identity or a unique element that such that 0 plus a equals a, which is, again, may seem obviously true, but these ground rules are very, very important. 6. Existence of the multiplicative identity. There's a unique element 1 in R such that 1 is not equal to 0 and 1 times a equals a for all a in R. And again, this is saying sort of a similar thing just for multiplication. There is one number in every field such that a times that number is equal to a. And this there's different situations where it's not always 1 and where 0 is not always the additive identity. And I'm sure we'll get into that later. I've learned a little bit about that in linear algebra. There's times when 0 is not the additive identity, which is really freaking cool. Existence of an additive inverse. For every x in R, there's a unique element, negative x in R, such that x plus negative x equals 0, which is cool. You can use it in proofs, and you can use all of these in proofs. These are the field base axioms. You can use them in pretty much any proof that you do, and they're really cool to use. 8. Existence of a multiplicative inverse. For every x in R that is not 0, there's a unique element x inverse, the inverse x in R, such that x times x inverse equals 1. And usually this can also be written as 1 over x, right? X times 1 over x equals 1. And this is just the multiplicative inverse. So we can derive basic algebraic laws from these axioms, including 1, negative 1 squared is equal to 1. 0 times a equals 0. Negative a equals negative 1 times a. Negative times negative a is equal to a for all a in R. 3, negative a minus b is equal to b minus a. 4, a, b, and r. For all a and b and r, a times b equals 0 implies that a equals 0 or b equals 0. And again, these all seem obvious, but they are all derived and proved by these basic field axioms, which is really cool, and the proofs are really cool. These axioms do not fully define the real numbers, so to do that, we need a second postulate. So this is the second postulate, the order axioms. There's a relation less than on, this is just the sort of alligator symbol that you learn about that says less than, on R cross R, or R2, which has the following properties. 1, the trichotomy, I don't know how to say that word, trichotomy property, trichotomy property, it's a stupid word. Given A and B are in R, and one and only one of the following statement holds. A is less than B, B is less than A, or A is equal to B. Given two numbers, all this says is that given two numbers, one of the following is true. A is less than B, B is less than A, or A is equal to B, right? If you have the numbers 1, 2, well, 1 is less than 2. If you have the numbers 2, 3, well, 2 is less than 3. Or if you have the numbers 2, 2, 2 is equal to 2, right? Only one of them can be true at a time. The transitive property. A is less than B and B is less than C implies A is less than C, right? If A is less than some number and that number is less than some other number, A is less than that number, right? If 2 is less than 3 and 3 is less than 4, well, then 2 is less than 2, or 2 is less than 4. The additive property, A is less than B, and if C is in R, imply A plus C is less than B plus C, right? If you manipulate an equation on both sides or an inequality on both sides, nothing really changes. The multiplicative property, A is less than B and C is greater than 0, right? You have two cases here. So A is less than B and C is greater than 0 implies that AC is less than BC. The second case is when C is less than 0. This implies that BC is less than AC, because when you have a scalar multiple that is less than 0, so it's negative, the inequality flips, right? A is said to be non-negative if A is greater than or equal to 0, and A is said to be positive if A is strictly greater than 0. So let's get into some subsets of the real numbers. So first we have the natural numbers. This is equal by definition to 1, 2, 3, 4, all the way up to infinity. This is all the positive integers, and it's called the natural numbers. So then we have z, which is all the integers, and this is equal by definition to negative infinity to infinity, not included, and it's every single integer, right? Every integer, there are no decimals, it's just every sort of counting number. Q is equal to definition by m over n, such that m and n are in z, and n does not equal 0. So this is all the rational numbers. Every rational number is a number that can be divided, can be represented by a simple fraction. So this is every integer. Pi is an example of an irrational number. Pi is not in this set because pi cannot be represented by a simple fraction. Some people represent pi as 22 over 7, but that doesn't fully get to the infinite digits that pi has, right? So pi is not in this set. And the same with square root 2, because they cannot be represented as simple fractions. And if you want me to prove that, I can't prove that pi is an irrational number. It's a huge proof that I haven't learned and that I don't know. I can prove that square root of 2 is an irrational number. So if you would like me to do that proof, let me know. The complement of Q, such that R is not Q, is the set of all irrational numbers. So all that says is that every number that's not a rational number is in that set. So that's right, just I was saying, every number that can't be represented as a fraction. Equality in Q is defined by m over n is equal to p over q if and only if mq equals np. And that's just defining what equality is. So these are all proper subsets of the next. So n is a proper subset of z, and which is a proper subset of q, which is a proper subset of r, which is really interesting to think about. And here's a remark. We assume that n and z satisfy the following properties. 1. Given n is in z, one and only one of the following statement holds. N is in z, negative n is, or n is in n, negative n is in n, or n equals 0. So this is saying for every integer, so every number in z, only one can be true. N can either be in the natural numbers, negative n can be in the natural numbers. So if you had any negative integer, the negative of that number would be in the positive integers, so n, or n equals 0, because 0 is not a part of the natural numbers. If n is in n, then n plus 1 is in n, and n is greater than or equal to 1. That's because every number greater than 1 is in the natural numbers, right? We already stated that every positive integer is in n. So if n is greater than or equal to 1, then if you add 1 to that, it's also in the natural numbers. 3, if n is in n and n is not equal to 1, then n minus 1 is in n. So if you had 2, 2 minus 1 is 1, which is in n. Any number greater than that is also in n, right? So that's just saying that if you have a number greater than 1 in n, if you subtract 1, it's also in n. 4, if n is in n and n is greater than 0, strictly, then n is also in n. That's just saying every positive integer is in N. Notice how none of R special subsets satisfy the postulate, right? This is where I got to in the book, but it says here that N satisfies all but 3 of the properties in postulate 1. N has no additive identity since 0 is not in N. N has no additive inverse because -1 is not in N, for example, and only one of the non-zero elements in N, namely 1, has a multiplicative inverse. Z satisfies all but 1 of the properties in postulate 1. Only 2 non-zero elements of Z have multiplicative inverses, namely 1 and -1. The rest don't because there are no rational numbers, right? 2 has no multiplicative inverse because 1/2 is not in the set of all all integers. QC, which is just the complement of Q, so all the irrational numbers, satisfies all but 4 of the postulates in all of the 4 of the axioms in postulate 1. It does not have an additive identity since 0 is not in the irrational numbers. It does not have a multiplic identity since 1 is not in the irrational numbers. It does not satisfy either closure property. Indeed, since the square root of 2 is irrational, the sum of irrationals may be rational, right? Square root of 2 plus negative square root of 2 equals 0, which is a rational number. 0 is a rational number, which is pretty interesting. And the product of irrationals may be rational, right? Square root of 2 times square root of 2 is 2. That is not closed under addition or under multiplication, therefore it is not a field. Notice that any subset of R satisfies postulate 2. Thus, Q satisfies both postulates 1 and 2. The remaining 2 postulates introduced later on identify properties which Q does not possess. So we will learn that Q might not be a field because it doesn't satisfy later postulates that I have not gotten to yet. And that's all I've gotten to today. I'm about halfway done with section 1.1, and when I finish, I will make a new video finishing 1.1, and then I will start with 1.2. Thank you. This is my new series on real analysis. Let me know if you're interested for me to make new videos. I'm Ben, and this has been Math with Ben, and I hope you have a great rest of your night.